Next, we'll talk about all the set operations, and they are union, intersection, set difference, and complement. For each of them, we'll give the definition, the set description, and we'll see some examples. First, union. The union of set A and set B, denoted by A union B, is this set. You can see each element in the set is either an element of A or an element of B. Let's see one example. If A is this set, B is this set, then what is A union B? We know that each element is either from A or from B. Therefore, we can first copy down all the elements in A. Then we'll look at B. 3 is already there, since we know that for the set, each element only appears once. And 5 is there too. We don't have to write 5 again. 6 is now there, so we write down 6. 10 now there, we write down 10. 11 now there, we write down 11. So this is A union B. And before we move on, I want to introduce this concept, Venn diagram. It is named after an English mathematician, John Venn, here. A Venn diagram is used to visualize all possible relations of sets. And to show this relation, we have to introduce this concept called universal set. We say a set is the universal set if this set contains all the objects or the elements under consideration. So if you are studying integers, then S is the set of all integers. If you are studying Mine students, then S is the set of all Mine students. Okay? And for Venn diagram representation, we usually use a square to represent the universal set. And then we use circles to represent its subsets. For example, A is this circle, and B is another circle. And then, if you put A and B together, this shaded area represents A union B. As you can see, we can also use this Venn diagram to represent the possible relationships between sets. For example, if A is this set, then we know B is a subset of A. We can represent this relation this way. Next, we'll move on to talk about more set operations. The second one is intersection. The definition is the intersection of A and B, denoted by A intersect B, is given by this set. You can see now each element in the set must be an element of A and an element of B. So different from union, where you require is an OR relation, here is an AND. Therefore, for the same example, A and B, A intersect B is, how do we know what elements should be in the set? What you need to do is you need to find the common elements in A and B. You can see 3 is one of them, 5 is the other one. And we don't have any more common elements. Therefore, A intersect B only consists of 3 and 5. And we can still use the Venn diagram to show this operation. Here, the shaded area is A intersect B, because this is the set of elements that are in both A and B. The third one is set difference. The set difference of A and B, denoted by A set minus B, is described this way, where each element is in A, but it's not in B. So equivalently, you can think of it as you remove all the elements in A if they are in B. And based on this definition, we can have this equation. A set minus B is equal to A set minus A intersect B. Why? We can first use the Venn diagram to illustrate it. Then we can prove this equation later on. This is the Venn diagram, and this is A set minus B. You can see it consists of all the elements in A, but not in B. And what is A intersect B? It is this area. And you can see if we want to represent A set minus A intersect B, we basically remove all the elements in the intersection area from A. Then we have the same shaded area. So using this Venn diagram, you can see this equation holds. But later on, we can formally prove this equation. Next, let's see one example. Again, we use the same examples for A and B. And to write down A set minus B, what we need to do is for every element in A, we check whether it's in B. If it's also in B, we remove it from the set. Okay? 1 is in A, but it's now in B, so we can write 1 here. 3 is in A, but it's in B, so by definition, it should not be in the set A set minus B. 5, no. 7, in A, but not in B. 9, in A, but not in B. That's it. This is A set minus B. Now let's see some very interesting relationships between set difference and intersection. First, let me introduce another concept. We say two sets A and B are disjoint if A intersect B is empty. In other words, A and B do not share any common elements. Based on the definition, if A and B are disjoint, then A set minus B is equal to A. Why? By definition, A set minus B is the set of elements which are in A but not in B. Since A and B are disjoint, we know that they don't have any common elements. Therefore, A set minus B is just A. Similarly, B set minus A is just equal to B. We can also show this using Venn diagram. This is a universal set S, and since A and B are disjoint, they don't have any overlapping area. Now you can see A set minus B is just the A, and B set minus A is just B. Second, for any two sets A and B, A set minus B and B set minus A are always disjoint. Let's use the Venn diagram to show it. This area is A set minus B. This area is B set minus A. And you can see these two shaded areas do not have any overlaps. Therefore, they are disjoint. Here that even though you can see I use Venn diagram to illustrate the relations, you're not supposed to use Venn diagrams as a proof. Next operation is called complement. Let A be a set of the universal set, then the complement of A, denoted by A prime, is given by this set, where each element is in the universal set but is not in set A. In other words, the complement of A is the set of elements which are not in A. Let's see one example. If S is the set of non-negative integers, and A is given by this set. Can you see what A is? A is actually the set of all non-negative even integers. And therefore, A prime is the set of all non-negative odd integers. Each odd integer can be represented by 2k plus 1, where k is a non-negative integer. Here note that the first property of X is actually redundant. If you remove them, A will still be the non-negative even integer set. A prime will still be the non-negative odd integer set. And using Venn diagram, if this is A, then this shaded area is A prime. Using the complement concept, we can rewrite the set difference as this way. Basically, we are replacing the second property of X, not in B, but X is in B is complement. Therefore, A set minus B is equal to A intersect B prime. Next, we're going to use a Venn diagram to illustrate that they are indeed equal. On the left side, you can see the shaded area is A set minus B. On the right, let's see whether A intersect B prime is the same shaded area. First of all, this is B prime because B prime consists of all the elements not in B. And this dark area is A, and you can see A intersect B prime is this area. And you compare the left side and the right side, you can see A set minus B is the same as A intersect B prime. Again, here I'm using the Venn diagram to illustrate the relation. We are not supposed to use Venn diagrams as a proof. Here are some exercise questions. You can use them to practice your understanding of the set operations.